Hey everyone, my name is Alex Tomsick. I'm the Director of Engineering for Red Wolf Reliability. This is a video that's part of a series on our Voyager FDS sensor. If you haven't seen the other videos in this series, please go to our website and feel free to watch them if you can. This video specifically is going to talk about how strain differs from acceleration using a cantilever beam as an example. Before we get to our demonstration, I just wanted to kind of talk about a couple points. The first being what we may expect to see from our cantilever beam demonstration between acceleration and strain. So the image on the top right shows a cantilever beam similar to what we'll look at in our demonstration. It's fixed on the left side and it has a force that pushes it down on the right side. That force that pushes down on the right side causes deflection on that end of the beam downwards, and the fixed side can't deflect because it's fixed in that direction. So the bending of that beam causes stress to build up in the beam, and it ends up causing, in this configuration where the beam is being pressed down, it ends up causing tensile strain to develop in the top half of the beam and compressive strain to develop in the bottom half of the beam. When that beam is released, you get oscillating strain as the free end of the beam fluctuates from being down to up. You'll actually end up getting a change in that strain where the top side that was in tension will go into compression, and the bottom side, which was in compression, will go into tension. This will show up in the strain data from the FDS sensor. One important thing to note is the strain will be highest on that fixed side of the beam, and you'll see almost no strain amplitude on the free end since there's nothing to resist on that side. Now, in comparison, acceleration should be really high on the right side of the beam, the free end, because that's where you have all of the deflection, while the left side of the beam should have very little acceleration since it can't deflect like the free end can. In the first couple videos in this series, we talked about how to calculate strain and what strain conceptually is. But the amplitudes or magnitudes of those strains that we calculated in the previous videos were really large compared to what you may actually see in the real world. In general, strain amplitudes are very, very small. For example, on a hydrodynamic bearing, it's typical that you may see an amplitude of 5 millionths of a strain. Given how small these amplitudes are, it's very difficult to work with these numbers. So what we do is we scale those values by a factor of a million to get to a scaled unit that we call microstrain, where micro is denoted by the mu and strain is the epsilon. So for example, say we have a value of 5 millionths of a strain. If we multiply that by a million, we would get a value of 5 microstrain. So it's the same number, it's just scaled to make it easier to work with. So now I want to give an example of a calculation using microstrain to then relate it back to some physical dimension, just to show you where these values are coming from when we use the FDS sensor. So let's take the example below. We have the FDS base plate, which is approximately half an inch long. That base plate is what gets adhesively mounted to a beam or whatever you're trying to measure. And say the FDS sensor measures a strain amplitude of 9 microstrain. We want to calculate how much that length of the base plate has changed based on the strain. So down on the lower left, we have an image of the base plate that we can use to kind of conceptualize what we're looking for. Now, if we take that 9 microstrain and we first divide it by a million, we'll get to the actual strain value, which would be 9 millionths of a strain. And then if we multiply that 9 millionths of a strain by the original length of half an inch, we'll get to the change in length of that base plate being 4.5 millionths of an inch. So I wanted to kind of give this example to show just how small the dimensional changes we're talking about are for us to measure strain. Hey everyone, so here we have a cantilever beam demonstration. From the first slide in this video, I talked about how strain will develop in this cantilever beam at the fixed end. You should see the highest strain at the fixed end,
with little to no strain at the free end. Right, that's because when you bend this beam, you have a moment that's resisted only at this fixed end. So we're going to try and demonstrate that with collection of dynamic strain data, and then we're going to also show a comparison of what acceleration data might look like on this beam. So here we have our Voyager FDS sensor. Typically this would be adhesively mounted, but for the purposes of this video, since we're going to move locations, we're going to just mount it with a magnetic fixture. So first I'm going to mount this at the free end of the beam. Now remember, if we were to pluck this beam and displace it from rest, this beam is going to vibrate at the first natural frequency of the beam. So we'll pluck it. I'm going to show some data down in the corner of this video. And there should be relatively low strain amplitudes. The FDS sensor is very sensitive, so there likely will be some seen in the data. But now if we move it out to the fixed end, and we pluck the beam again, you should see much higher strain amplitudes on the fixed side of this beam than the free side of this beam. Now if we make the same comparison with acceleration, this is just a small, lightweight 100 millivolt per G accelerometer. So I'm going to place it on the fixed end of this beam. It's just being held on with some wax. Pluck it. You should have very low acceleration amplitudes on this end of the beam. Now if we move that to the free end of the beam, where all of the displacement's happening, if we pluck it again, you'll notice that the acceleration amplitudes are much higher on the free end of this beam. The reason that the acceleration amplitudes are higher on the free end of the beam is because there's displacement on this end. In order to have high acceleration, you have to have high displacement. The fixed end of the beam has very low displacement amplitudes, and so you'd have extremely low acceleration amplitudes. So now just for comparison's sake, since we know that we expect high acceleration on the free end of the beam and high strain on the fixed side of the beam, I'm going to mount the FDS sensor on the fixed side, and then we'll keep our accelerometer on the free side, and we'll just show some comparison time domain data between these two. Okay, so we'll discuss this a little bit more when we get back to the slides. Thanks.
Welcome back. I just wanted to show the data from our example demonstration a little closer up. I know it was at the bottom of the screen in that demonstration video, but it went by really fast. So I just wanted to kind of slow down and show it in a little more detail and talk about it a little bit more. So first we're going to look at the strain time waveform collected at the free end of the beam using the FDS sensor. If you notice, when I displace the beam from rest, you see a very, very small increase, a very, very small change in strain, and you get a ring down event. This will become more apparent when we look at the bottom time waveform, which is the FDS data collected at the fixed end of the beam. So here at the fixed end of the beam, right, these are on common scales. It goes from 3 microstrain to -3 microstrain. The fixed end of the beam has much, much higher strain amplitudes than the free end of the beam, just like how we expected. Another important thing to talk about is notice that the strain amplitude goes up initially to a positive value before oscillating at the beam's first natural frequency. So remember from the video, I pulled down on the beam to displace it from rest, and then we measured the response. By pulling down, the top of that beam where the sensor was mounted would be in tension. A positive strain value from the FDS sensor shows that the beam was in tension. So you can see that that stress on the top half of the beam, or sorry, the strain on the top half of the beam oscillates between tension and compression as the beam vibrates at its first natural frequency. If we look at the same time waveforms for our accelerometer, we'll talk about the difference as well. So first we're going to look at the acceleration time waveform collected at the fixed end of the beam. So you can see when the beam was disturbed from rest, you get a very small change in acceleration with a very, very small ring down event as the beam vibrated at its first natural frequency. Now if we look at the acceleration time waveform from the free end of the beam that was able to move and displace, you'll notice that on a common scale, you get much more acceleration at the free end of the beam. That's because you have to have displacement or the ability to move in order to have acceleration. Since the fixed side of the beam is fixed and not allowed to move, you don't see much acceleration at all. So finally, I just wanted to show a comparison of the time waveform collected from the FDS at the fixed end of the beam compared to the acceleration time waveform collected by the accelerometer at the free end of the beam. It's important to notice here that the time waveforms look very, very similar. That's because the time waveforms between those two are showing the same oscillation of the beam, it's just in a different unit system. What I wanted to really show here was it's really important to understand the difference between the two measurements to know where to collect, right? So typically for the FDS or an accelerometer, we're going to use it on rotating equipment, but this just shows that they're measuring response of that system. They're just measuring it in different ways. All right, everyone, thank you for watching this video. The next video in this series is going to provide an overview on fluid film bearing operating theory. If you have any questions or interest in the Voyager FDS sensor, please check out our website at voyagerdynamics.com. Thank you.